This is the first video for Power Engineering 1 module, that is EE114, and here we'll be talking about single phase AC circuits. So why do we need to study AC circuits? And the reason is that this is actually a long drawn out battle called the War of Currents between Edison, that supported DC, and Tesla, who supported AC. Technically Tesla won. We use AC nowadays, and the reason is that AC has lower power losses in the transmission line. So if you have very long transmission lines, you have to prefer AC because it has uh, very less power loss compared to DC. Now AC voltage is also much more easily stepped up or down. So during transmission you can step it up, and when you want to use it you can step it down. This is done using something called a transformer. The reason why it's much easier to use a transformer is that for DC you need to use semiconductor devices and things like buck converter and boost converter, and they also cannot sustain much more current or voltage. Instead AC voltage is much more easily stepped up or down. But in some places, like in very high voltage DC transmission line, HVDC lines, DC is still preferred over AC. And the reason is that in such high voltage conditions, almost all of the current spreads out into the periphery of the wire in AC only. This is called the skin effect, and this dramatically increases the resistance of the transmission line. So in such a situation, the power loss argument turns in the favor for DC, and that's why we start using DC. This is a common diagram that you must have seen during JE, which shows the difference between direct and alternating current, where direct current is a constant value and alternating current has an alternating value basically. Know that AC allows for multiple phases, and we will come back to what phases are in a later video, but right now we are going to stick to a single phase. Before we start talking about the sinusoidal quantities themselves, we need to try and simplify them. That is done using phasors. So what are phasors? They are simply a trick to simplify the sinusoidal quantities. Why do we need to simplify sinusoidal quantities? The reason is that try adding two sinusoidal quantities at random phases with having random lengths at the same frequency, and you will see that it turns into a major headache. It's very time consuming to try and fit the values, and if we keep doing that it's going to be very hard. It's going to be a major headache. So what we do is that we turn it into a complex number. So how do we turn it? We use, like, this is a general quantity. It could be the voltage, it could be the current, it could be anything. So let it have an amplitude AM, let it have a phase phi, let it have a frequency omega. So now this is a sinusoid, and when we go to the complex plane, this is represented as an arrow. The arrow has length am over root 2. This root 2 is what makes it an RMS value. Why RMS? It is helpful in power calculations. We'll come back to that. And the angle at which it is inclined to the x-axis is phi, this phase. Note that this is a complex number, so you need the square root of -1. And here is a disclaimer, we are going to use j for the square root of -1 and not I, because I is now current. We do not want any confusion. Also, A is a complex number now, so we are going to put a tilde over its head to keep in our mind that it is a complex number. And if you have a voltage source that is oscillating at 50 Hz in a circuit, the current also oscillates at the same frequency. It is oscillating at 50 Hz. All voltages in the circuit are oscillating at 50 Hz. All currents in the circuit are oscillating at 50 Hz. In this condition where everything is oscillating at the same frequency, you can add the complex numbers, and then what you get as the addition is the sum of those sinusoidal quantities. And this is actually very helpful because you can add and multiply complex numbers very easily. You just have to add their components, right? This allows doing the addition and multiplication of sinusoidal quantities without the hassle of using trigonometric identities. And there are something called the polar and Cartesian representations of phasors. And polar form is basically useful when you want to multiply them. Cartesian form is basically useful when you want to add them, right? Because then in multiplication you simply add the phases and you simply multiply the amplitudes. People in electrical engineering prefer this form for the polar form, where you bring the phi down and you put an angle symbol in front of it. Now it is helpful to mark the frequency with a curved arrow, and we will say in the last slide why we need to mark the frequency. Not always, but it is helpful, and why we will come to that. And here is a well drawn phasor diagram where I have taken the voltage as a basis. So the basis means that its phase is 0 degrees. Now the currents have some phases phi 1, phi 2, and if I try to add them, their net phase is some I. And I've tried to draw a parallelogram to show that these two phasors are getting added. Now as soon as I say that you can draw a curved arrow like this and put some number to show the frequency, I do not mean that the phasors rotate. They don't rotate. the sinusoidal quantity was cos omega t plus phi. Now I've accommodated for the cos omega t by making this into a complex number. I do not need to show that there is some time variation of this phi because this phi is now fixed in time. This phasor is not some snapshot in time and it's not rotating. This is a very common misconception and this is not what happens. This phasor is not rotating in time. Please note that. The usual phasors that you are going to deal with are the voltages and the currents. So we will see why. And before we do that, we need to understand that, you learned how to add sinusoids, you learned how to multiply sinusoids in the complex plane. So how do you differentiate and integrate sinusoids? And there is a very nice result in calculus that we will now use, which says that if you want to differentiate a sinusoid, it is same as adding a phase shift of 90 degrees to the sinusoid and then multiply the frequency omega to the amplitude of the sinusoid. So in complex plane, this is even easier to see. You simply introduce a 90 degrees phase shift to it, and then you multiply its length by the frequency omega. Integration is defined as anti-differentiation, so you can see what is coming. If you want to integrate it, you add a minus 90 degree phase shift and you divide its length by the frequency omega, right? And now since you have learned integration, differentiation and adding and multiplication of phasors, we can learn about Kirchhoff's laws and the phasor domain. So they were very helpful in DC circuit. They will be very helpful in an AC circuit also. Make sure that the quantities you use are complex numbers. But, well, the main thing that you use is V equal to IR. So you know a complex V, you know a complex I, but you don't know complex resistance yet. So that is called the impedance. And it accommodates for capacitors and inductors also, which in an AC circuit do not show their DC circuit behavior of tending to some value, or that in steady state capacitor does not allow any current to flow and inductor does not allow any voltage drop to occur across it. These two allow those things, but they start introducing phase shifts across the V and I in between them. Now Z is also a complex number. The impedance is a complex number, so we put a tilde over its head and we show it as R plus Jx, where R is the resistance, chi is the reactance, or X is the reactance. We will see what the reactance means. So now by the definition of Phasor Ohm's law, Z is V over I, all are complex quantities. So suppose we have a resistor, so we don't even need to put the tildes because V equal to IR. So R is simply the real value R. There is no phase shift for the impedance of a resistance. Now suppose you have I equal to C dV by dt. The dV by dt, as we know, differentiation of a phasor spits out j omega. So now you have j omega c. So across a capacitor, I is j omega c V, but that is V over Z. So the impedance of a capacitor is 1 over j omega c or minus j over omega c. Now note that this does not have any exponential thing in it, because in capacitors in usual we see that it starts exponentially decaying or something. That is not happening here. It's simply introducing a phase shift of 90 degrees. Similarly, if there is an inductor, V is L di by dt, you differentiate the current, it spits out j omega, so the impedance of an inductor is j omega L. Again, 90 degrees phase shift, no exponential behavior. So the real thing is always coming from R, because these two have only imaginary components. So the real part is the resistance. The complex part is a sum of these two. So this is called XL, this is called minus XC. The minus because it is negative. It is introducing a phase shift of minus 90 degrees. So the net complex or the net imaginary part X is XL minus XC, or j omega L minus j over omega C. Now series and parallel formulas that had worked for impedances and resistances yet, they will work, because now instead of using normal numbers, you can just use complex numbers, and all these formulas will hold because all these had been derived from Ohm's law and Kirchhoff's laws. All of them hold but in complex form, so all these formulas hold but for complex form. Similarly, Thevenin and Norton theorems hold. You can depict any linear circuit as a voltage source with a impedance in its series instead of a resistance. And superposition also works. Superposition even allows you to deal with voltage sources that have different frequencies. Suppose you have a circuit with two voltage sources and both of them have different frequencies. How do you deal with it? Superposition says short one voltage source and take the effect of one. So when you take the effect of the first voltage source, you draw the phasor circuit with its own frequency, you calculate the current, you convert the current back in time domain. Now you go to the second voltage source, you short the first one, you draw its phasor diagram, you find the current, and then you take its time domain representation. Now you have two time domain currents, and superposition says just add them and that's the final current, that's it. Now here is a warning about the impedance. We have been talking about impedance like it's a phasor because, well, it walks like a phasor, it talks like a phasor, it is a complex quantity, but no, it is not technically a phasor because it does not oscillate in time. Why? Well, suppose you have an inductor, the impedance of an inductor was j omega L, but that does not mean that it is actually a sinusoidally varying quantity that has some weird impedance that is varying with time like cos omega t. That is not happening here. What is happening is that phasor analysis has led us to a complex number that is the ratio of the voltage and the current. But that does not mean that the ratio is itself a phasor. It is not sinusoidally varying in time. It is just a complex number. And it is a very complicated complex number. And it will show some secrets later that will be very interesting because in power system analysis, it will actually become a very important part. So we will come back to that in the next video. Thank you. And this is the end of video 1.